Hello everyone and welcome to our session, What is Information? In the last session we introduced information theory, focusing in particular on entropy, the fundamental measure of information theory, which quantifies uncertainty. I hinted during that session that we would consider information as a reduction in uncertainty, and said several times that uncertainty and information were two sides of the same coin. In this session, we're going to make that definition more precise. In this short video, I'm going to introduce the session and start to introduce how we quantify information. So looking at the outcomes for the session as a whole, I want you to be able to express ideas about information and relate those ideas to uncertainty. So coming back to this fundamental idea that we can quantify uncertainty and then a reduction in uncertainty as information. In the previous session, we looked at some of the fundamentals of information theory, including entropy, joint entropies, and conditional entropies. We're now going to extend that and look at further fundamental measures, including mutual information and conditional mutual information. And I want you to be able to partially construct MATLAB code to be able to compute such measures and to apply that code to examples. That's something that will be done in activities, though, not specifically in the lecture here. Primary references for this lecture are as follows, with different sections from our four main references. Before we come to our definition of information, there are two other background definitions that I want you to be across. The first one is known as the cross entropy. The equation for the cross entropy looks very similar to what we already saw for the Shannon entropy, and there's a very good reason for that. The cross entropy quantifies the average code length that we would use to encode realizations of our variable x. The average code length that will be used if we use some probability distribution function q to come up with the coding for x. However, x has a different or actual PDF specified by little p. So let's see how we can make sense of that from the equation. What we see here, we recognize the log term tells us what the Shannon information content would look like if x were distributed as specified in the distribution Q. So if we followed Q, these are the code lengths we would use for each symbol little x. If we want to look at what average code length we would then use if we encoded our instances as per Q, then we need to average over all instances x, and we average across the way those x's are actually distributed, which is specified by p. Okay, so that's where the cross entropy is coming from. The average code length that would be used if we use the distribution Q instead of the real distribution P. And we've seen this sort of idea before when we talked about encoding the winners of a horse race and how we may decide just to use 2 bits to encode them, which would mean an equiprobable distribution Q, and then said, well, that may not be actually the same distribution that x actually has. So similarly, then we can look at the Kullback-Leibler divergence, which then takes a difference between the code length that would be used if we assumed there was a distribution Q that x was following versus the code length that would be used if we had used the true distribution P. So we can look at the Kullback-Leibler divergence as a coding penalty. It's simply taking the cross entropy and subtracting the Shannon entropy away from that. Okay? So it's a code penalty if we use the distribution Q to make the encoding, but the real distribution is P. Now here, the Kullback-Leibler divergence is always greater than or equal to 0. So we can't have a negative coding penalty on average here. Okay? Some of our realizations x may have a shorter code length under Q than they would have under P, but on average that's not going to be the case. On average we'll always have a coding penalty if we don't use the right distribution, and that's something that we hinted at when we looked at that horse racing example earlier. So now let's come to define information. We define information via the mutual information function. We talked about uncertainty a lot in our last lecture, and as I say, I already mentioned that we would look at information as a reduction in uncertainty. And this is exactly what mutual information is quantifying for us now. It's a reduction in uncertainty or surprise about one variable x that we obtain from another variable y. We can give a first interpretation of mutual information using the Venn diagrams that we looked at earlier. So here we looked at how we can represent the uncertainty in a variable x, the uncertainty in a variable y. We can look at the joint uncertainty in them as the sum of the areas. And we can look at conditional uncertainties, how much information is left in x if we already know y, and vice versa about y if we already know x. So there was a hint, effectively, that the crossover area here was what the two variables had in common. And that is exactly what the mutual information quantifies. It quantifies here the reduction in uncertainty about x, given that we already know y. It's this part that is the reduction. Mathematically then, we can write it down as follows. We write down, and you can understand all of these equations from the diagram here. We can write down that we sum the marginal entropies and take away the joint entropy, and what's left is this piece in the middle. We can think about starting with the uncertainty in x and then taking away the uncertainty that's left in x after we know y, again leaving this piece in the middle here. We can do the same thing if we look at the uncertainty of y and take away the uncertainty left in y after we already know x. What's important is the mutual information is symmetric. The information that x carries about y is the same as the information y carries about x. We can also see some of the fundamental properties straight from the diagram here. We can see that because we're dealing with areas here, the mutual information is always greater than or equal to 0. On average, we cannot be misinformed by y about x. We can also see that it's less than or equal to the minimum uncertainty in each of our variables here. The area in a subcomponent of either of them cannot be bigger than the smaller area of x and y. I've mentioned already that it's symmetric in x and y, and we can also see another boundary condition here. We could have that the mutual information between x and y is equal to the entropy of x. So this area here could be equal to the whole area of x, which basically says to us that the uncertainty in x is contained inside the uncertainty of y. That tells us there is no uncertainty left in x if we already know y. The next interpretation that I want to give you comes back to the Kullback-Leibler divergence, or equivalently takes a Bayesian view. We can dig in further to the equations that we have here for our mutual information. We can now see these equations result from the sums and differences of entropies that I showed you before. We can see then, we can write down the mutual information here as a Kullback-Leibler divergence between the true joint distribution of x and y and the distribution that they would have if they were independent. Okay, and that's what's represented in this property here. Mutual information is that Kullback-Leibler divergence. It's telling us what the code length penalty would be if we had to encode x and y jointly if we assumed that they were independent. Okay, so if we assume they're independent, what's the code penalty that we pay for making that assumption of independence? How much extra code would it take us to encode them in this way rather than using their true joint distribution? So if we use their true joint distribution, we don't have to encode their overlap twice. We just encode the common information in them once. Equivalently, we can use Bayes' theorem to rewrite this fraction in this way here. We can now look at the mutual information as the log ratio between a posterior distribution on x, given knowledge that we have from y, versus a prior distribution on x that does not take y into account at all. Similarly, we can think about this. We can think about this ratio as describing a code penalty. It's a penalty, it's a code penalty that we pay if we encode x on its own without using any information from y, versus the code length that we could use for x if we use the knowledge that we already have about y. Okay? They're the first two interpretations that I want to give you about mutual information. We'll have further interpretations in the next short video.